Hello, and thank you for downloading the latest Data Science Central podcast. This is Bill Vorhies, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. So in today's podcast, we'll be sponsored by Nvidia, and we very much appreciate Nvidia's support for the Data Science Central community, and we're honored to have them sponsoring our event today. Today's podcast will be about 15 minutes long, and we have one speaker who I'll introduce in just a minute. And today's talk is entitled Infrastructure Considerations for Deploying Deep Learning at Scale. Now, our speaker today is Tony Paikeday, who is the Director of Product Marketing for Nvidia Deep Learning Systems. Now, with over 25 years of experience in product management and marketing, business process and manufacturing engineering, Tony helps organizations infuse the power of deep learning to solve their most important business transformation opportunities. Tony holds an engineering degree from the University of Toronto. So Tony, thanks for being with us today. I understand you're going to talk about how organizations can infuse the power of AI into their business, and specifically in the second of two parts, we'll explore the productivity, performance, and cost considerations that should be weighed when deploying deep learning at scale in the enterprise, and how to avoid the pitfalls of short-term decisions that can negatively impact your long-term AI strategy. So Tony, let's get started. First question, what challenges do you hear most often from organizations wanting to deploy production deep learning?
Thanks, Bill. Most teams that I talk with often start with a similar mindset or considerations for how they want to deploy. And these are often, I think, the result of external factors or pressures that can sometimes push us into short-term approaches. The challenge is that what seems like beneficial short-term decisions can have, this long-term lasting impact to our infrastructure path, and whether an enterprise will ultimately be able to meet their scale and performance objectives as their application takes flight. So I like to net this out to three common things that we hear like all the time. First, most teams have a time sensitivity, and they need demonstrable results now or even yesterday. This is compounded by management teams having this perception that just because you've invested in a data science team, success should be just around the corner. And there's, obviously a lot more to it than that. Second, every team wants to maximize the performance they get out of their GPU investment. Namely, they want to know that not only will the platform deliver results and speed of iteration, but it'll scale predictably. Now, however, this is actually counterbalanced with probably the third sentiment shown here, namely that they want it to be done at the lowest cost possible. So when it comes to platform, a GPU is a GPU, right? You put 4 or 8 of them in a box, add some freely available open source software, and you're done. Well, it sounds like a low-cost proposition, but when we talk about cost, it should include some understanding of the cost of productivity and the lack thereof, along with the cost of manageability and support, and what the penalty is for a system outage or degraded performance. So in reality, actually all three of these expectations are the right ones. And interestingly enough, they all have an implication for the TCO of a deep learning system. So these are the reasons why we built the NVIDIA DGX portfolio of AI supercomputers, offering integrated, full-stack AI solutions, which we introduced to our audience in our previous episode.
Well, Tony, thanks for that explanation. Now, what exactly is full-stack optimization, and why is it important for AI?
I think too often when folks are considering a deep learning system, they're lured into the trap of lining up the spec sheets, for instance, of various server platforms, and they assume that if the specs match and once they install some GPUs, then the performance will be the same and that the day-to-day operational experience will be the same. But I'd go further to say that many teams look at their server and, combined with an open source framework and commonly available libraries, expect that they've got a usable stack. But When we think of an AI stack, we're looking at everything, inclusive of every layer of software, from the framework to the libraries, the communications primitives, and the drivers, as well as the operating system image, and the GPUs, and the topology used to connect them. So additionally, there's also this underlying server configuration, including the CPUs that have been chosen, the RAM, the I/O, the disk, and the network. And if we're thinking about this really holistically, there's still the adjacent infrastructure inclusive of networked storage. So maybe it's no wonder that many will deploy a chosen config, install their software, and deploy a model that worked great on 1 or 2 GPUs, but suddenly, when they deploy the same model on this new platform with 4 or 8 GPUs, there's this total lack of linearity in terms of the performance boost. Now, they're not seeing the training speed drop from a 4th or an 8th like they had maybe expected. The reality is that deep learning training is impacted by a lot of potential bottlenecks that can exist in the system architecture, at which point adding more GPUs yields diminishing returns, or rather marginal increases in overall training speed. So with NVIDIA DGX, we basically looked at the confluence of all of these layers and engineered the complete hardware and software stack to ensure one key thing, that the brains of the platform, namely the GPUs, are kept busy 100% of the time, and that we're reaping the maximum performance from those GPUs, resulting in the fastest deep learning training speeds possible for each of the most popular frameworks that are out there today. And we do that such that developers don't have to be systems integrators, so they don't have to be software engineers, and just importantly, so they don't have to moonlight as IT support. This is why the NVIDIA DGX portfolio of AI supercomputers was created.
Well, Tony, thanks for that explanation. Now, GPUs can already be deployed on many common servers, and when you combine that with readily available open source software, isn't it more cost-effective to just build one's own deep learning platform?
I love this question. Remember the sentiment, I need to get the most GPU at the lowest cost possible. I mean, after all, if you can get your hands on GPUs, assuming cryptocurrency miners haven't taken them all, you could build a platform, right? Well, here's what that really looks like when you consider all the work that's truly involved in standing up your platform. And the blue parts shown here are basically what I call the sweat equity, or labor expended by your valuable data science team, spent on stuff other than practicing data science, namely engineering framework code, wrestling with open source software churn, and playing the roles of systems integrator. The green is the platform CapEx. And I think too many teams realize that by the time they've stood up a platform that meets the scale and performance demands of their AI use case, they've wasted months on things that have nothing to do with building better applications. And they've realized too late that the hours of lost productivity have a dramatic cost impact associated with them. Now, this is what happens when you deploy a full-stack optimized AI solution, namely the NVIDIA DGX. The non-value-add activities that have nothing to do with data science drop off your timeline, and your team's time and effort is solely focused on productive experimentation and insights. And because you've saved a ton of OpEx, your TCO is actually lower than if your team tried to take on the role of stack developer and systems integrator. And you get one very important additional benefit. That benefit being a dramatic compression of your timeline. All the time saved from non-value add work means the workflow that we talked about executes in a much shorter time frame, which means that you can iterate more, develop better models, drive up accuracy and performance, ultimately delivering a better product or service to your customers. A great proof point of this is the impact of, namely, a full-stack AI solution and the performance gains that it yields over a do-it-yourself approach. Now, what I'm showing here are two examples from organizations we've worked with, both of whom started with homegrown AI stacks. In both instances, you see where they felt they had a mature, optimized environment. And when we worked with them basically to move their models to our optimized stacks using our framework, library, and driver optimizations found on the Nvidia DGX, they saw a dramatic uplift in training speed, which meant up to 2x greater productivity for their developers, which directly impacted their ROI on their AI investment.
Well, Tony, thanks. That was quite an eye-opener. What best practices has Nvidia learned from its customers who've deployed deep learning at scale?
You know, we've spent a lot of time in the data centers of some of the world's largest AI hyperscalers, organizations that have vast CapEx, OpEx, and resources to, do groundbreaking work in AI that the entire industry benefits from. So these organizations, interestingly enough, selected NVIDIA DGX as their platform for very large-scale deployments, often dozens to hundreds of nodes. And through that experience and our partnerships, we've established some best practices that every organization can employ regardless of size or embedded expertise. Now, if I use autonomous vehicle system development as an example, we know that the number and complexity of the models used to power, for instance, a self-driving car, combined with the volume and speed of ingested data needed for training, demands an immense compute footprint. So when you're thinking about such large or maybe more even modest environments, there are some best practices to consider. For example, carefully designing your racks for higher density and power. You should expect that unlike traditional web or application servers, your GPU servers will continuously run at close to operational spec. This is not unlike what you'd find in other high-performance computing environments, for instance. Also, networking in between the nodes in the cluster requires very high bandwidth and low latency, especially in support of multi-node training. So think about either InfiniBand or 100 gigabit Ethernet network fabric using what we call RDMA over Converged Ethernet, or RoCE. Because of the volume of data to ingest and it being so massive, the network fabric is critical. But make sure, in addition, that the storage itself can support high I/O per second, or IOPS, especially at the beginning of a training run when the data is pulled into the onboard cache of the DGX. Storage performance and scale is also critical when you're running multiple experiments in parallel. Also, GPU nodes, as I mentioned, will run higher rack power than what you're used to, obviously running closer to operational spec, but you'll benefit from the efficiency of tapping more compute per watt. And because of this, you'll observe dramatically less floor space consumption in your data center than traditional CPU clusters. And I guess finally, when it comes back to software, you need to make sure that your full stack is optimized for multi-node cluster-aware training. This is probably one of the key optimizations in our DGX stack. And engineering that on your own, if you were to try to do so, could potentially waste months of effort. So there's a lot to consider, but this is what the NVIDIA team essentially wants to help simplify for our listeners.
Well, Tony, thank you. So finally, how can our listeners get more prescriptive guidance on how to scale deep learning within their existing IT?
Clearly there's a lot going on. But our charter, our mission, has been to democratize not only the platform and the infrastructure, but the knowledge required to design, deploy, and operate it. For that reason, we've started to offer prescriptive guidance that any enterprise can follow. We call these reference architectures or validated designs, technical white papers, and other assets, really recipes that anyone can follow, which are backed by proven performance and published results. the outcomes one gets from these DGX recipes or guidebooks are essentially a faster deployment experience, since you're not wasting time with design complexity and guesswork, and you get this simplified ordering experience, in fact, through our partners using modular units of infrastructure that can be turned up quickly. Second, you get linearly predictable scale through a proven design that ensures you can grow efficiently and cost effectively. And third, you get a simplified operations model with a single point of contact for production support, since our partners have expertise in the complete end-to-end stack, inclusive of not just the DGX server, but also the storage and networking and the AI software stack running on it. You eliminate finger pointing and having to scour open source forums for answers, and instead, you get a 24/7 enterprise-grade support model that keeps you up and running. I've provided some handy links here that take you to our DGX design documents and best practices, as well as some of the recipes that I mentioned built in partnership with our ecosystem. And this is a continually evolving offer. We'll obviously be talking about more additions to this portfolio as it grows after time. So I would highly encourage our viewers to check these out, share them with your IT team, and start to collaborate on how to build an AI infrastructure that meets your business objectives now and in the future.
Well, Tony, thanks. That was a very interesting discussion. And I'd like to thank Nvidia again for sponsoring today's DSC podcast, and particularly our speaker, Tony Paikeday, for his insight into today's topic. This is Bill Vorhies. I'm very pleased to have been your host for today's event. I look forward to seeing you all again at our next DSC podcast. Have a great day.